Hey guys, Mr. Betts here. As I've mentioned before, usually when we're taking antiderivatives, it's going to be for the purpose of evaluating a definite integral. So I want to look at how a definite integral is going to look with integration by parts. One thing we have to be careful about with integration by parts is that when we take an antiderivative, we have a way of using that integration by parts formula. However, if we switch over to doing a definite integral and we have limits here, it would not be okay to say that this expression, this definite integral here, is equal to this expression right here, even though this antiderivative is correct. And the reason is, remember that a definite integral represents an area, and an area equals a number, but this part of the expression right here is not a number, but it's a function. So it wouldn't be okay to say something that's supposed to be a number is equal to a function. Now, this part right here is a number because it itself is a definite integral, but we need to be careful about this. I should not put an equal sign between expressions like this when they are not actually equal. So I want to look at a couple of options of uh, how we can arrange our workflow so that we're not doing something illegal with our work. So one option is to keep the limits throughout our evaluation. So we're going to choose, using integration by parts, we're going to choose u and dv. I'm going to choose u equals x and dv equals cosine of x. So du equals dx, cosine of x dx. So v is going to be sine of x. And so using the integration by parts formula, just ignoring the limits for now, this expression is going to equal u times v, which is x times sine of x, minus the antiderivative of v du, so sine of x times dx. So this is the antiderivative or the indefinite integral. So using this first option here and keeping the limits on our expression, what we need to do is not only include our limits here, but we also need to include them here. So by using this evaluation bar and showing that we're evaluating this expression from 0 to pi over 2, now this is a number and this is a number. So the type of answer we're getting from this expression is what we expect. Then completing this problem, some people like to hold off and evaluate this later once we have the antiderivative here. Some people like to do as much as they can in each step with each part of it. Doesn't matter which way you like to do it. I'm going to go ahead and evaluate this expression as I evaluate this here. So we're going to have pi over 2 times sine of pi over 2 minus 0 times sine of 0 minus, and then for this part, the antiderivative of sine is the opposite of cosine, and that's evaluated from 0 to pi over 2. So doing a little simplifying, sine of pi over 2 is 1. So that first term is just going to be pi over 2. Second term is, it should have been a 0 there. So second term is 0. Then we're going to have plus, so negatives become a positive. Cosine of pi over 2 minus cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. So we're going to get pi over 2 minus 1. All right, so again, one way to do it, we're going to keep the limits on throughout the evaluation of the problem. But if I go back to what I said we should not do, notice that we don't have the limits on this expression here, but we can fix that by just adding them there. The other option is to do side work and evaluate the antiderivative in side work, and then come back and use that answer we got for the antiderivative in our side work to help us with the definite integral. So the way that would look, we want to start by writing the indefinite integral that we're evaluating. So I'm just writing this definite integral without the limits, which makes it an indefinite integral. Then we make our choices just like we did before. And we use our integration by parts formula. So u times v is x times sine of x minus v du. And so that's x sine of x plus cosine of x plus c. Now, if I'm doing this in side work, all of my side work here is an indefinite integral. So I want to make sure that I do that correctly, including the plus c. But then when I go over to evaluate my definite integral, remember I can use any antiderivative of this expression, which this right here is an antiderivative if c is 0. So I can rewrite this as x sine of x plus cosine of x evaluated from 0 to pi over 2. And then we plug in the pi over 2. Plug in the 0. And evaluate. Cosine of pi over 2 is 0. Sine of 0 is 0. Cosine of 0 is 1. And we get the same answer. Okay, so notice again that the integration by parts work that I did using this method was an indefinite integral over here. So I did all of my work complete for an indefinite integral, including identifying my work by saying what it is I'm evaluating to begin with. And then I took my answer here and I used that as the antiderivative here with my definite integral.